Everyone knows the story of railroad progress as a march toward bigger, stronger, more powerful locomotives. More tonnage hauled, steeper grades conquered, longer trains pulled across endless horizons, but buried in the archives of American railroading sites a machine that turned that logic inside out. A locomotive so powerful, so massively built, that railroad companies took one look at the engineering marvel they'd commissioned and said no. Not because it didn't work, not because it failed, but because it succeeded too well. The machine weighed over 1.2 million pounds. Its driver stood 8 feet tall. Its boiler could generate steam pressure that made veteran engineers nervous just reading the specifications. On paper, it represented the absolute pinnacle of steam locomotive design. In reality, it became a cautionary tale about the gap between engineering ambition and operational reality, a gap measured not in feet, but in thousands of pounds per axle, and the sudden, catastrophic failure of century-old infrastructure. This is the story of the locomotive that was too heavy to run. The year was 1944. World War II had stretched American railroads to their absolute limits. Every day, thousands of tons of war material moved by rail. Tanks, aircraft parts, munitions, troops, food, fuel. The Pennsylvania Railroad, one of the nation's largest carriers, faced a crisis. Their heaviest freight locomotives were working around the clock, and they weren't enough. The railroad needed more power, not incrementally more, dramatically more. Their chief mechanical engineer submitted a proposal that bordered on the insane. Build a locomotive with 6 driving axles instead of the standard 4. Equip it with the largest boiler ever fitted to a reciprocating steam engine. Design it to pull 16,000-ton trains over mountain grades that currently required multiple locomotives. Make it so powerful that it could replace 2 or even 3 existing engines. The board approved it. The engineering team got to work. And nobody asked the obvious question: what happens when you concentrate that much weight in a single machine? The locomotive that emerged from the Pennsylvania Railroad's Altoona works in late 1944 looked like something from a fever dream. Its wheelbase stretched over 122 feet, longer than some passenger coaches. The boiler, a massive tube of steel and rivets, ran nearly the entire length of the frame. 6 massive driving wheels on each side, each 8 feet in diameter, connected by a forest of side rods and valve gear that looked like the skeleton of some industrial dinosaur. The numbers told their own story. Tractive effort, 108,000 pounds. Boiler pressure, 310 pounds per square inch. Weight on drivers, 628,000 pounds. Total weight, 1,227,000 pounds, more than 613 tons. For context, a fully loaded semi-truck weighs about 40 tons. This locomotive weighed as much as 15 of them. The test runs began in February 1945. On the Pennsylvania's main line east of Altoona, crews fired up the monster and opened the throttle. The result was everything the engineers had promised and everything the operating department had feared. The locomotive pulled. God, did it pull. On grades where helper engines were standard practice, it climbed alone with 14,000 tons trailing behind. On level track, it accelerated freight consists that normally required 2 locomotives. The steam generation was flawless. The machinery ran smooth. Every technical specification was met or exceeded. And then the track inspectors filed their reports. Where the locomotive passed, Rail joints showed unusual wear. Cross ties cracked under loads they'd never been designed to handle. On curves, the outer rail showed stress fractures. Bridge engineers examined the structures after heavy trains crossed and found deflection measurements that made them pale. The locomotive wasn't just heavy, it was concentrated heavy, putting forces through individual axles that exceeded the design parameters of infrastructure built decades earlier. The Pennsylvania Railroad had a problem. They'd built the most powerful steam locomotive in their history, or possibly in American history, and it was slowly destroying their own railroad. The crisis came in April 1945. The locomotive was scheduled for a demonstration run for railroad officials and military observers. The route included the Rockville Bridge near Harrisburg, a stone arch masterpiece completed in 1902. Track engineers ran the calculations. The bridge could handle the weight, barely, but only at reduced speed and with specific positioning of the locomotive's weight. They posted speed restrictions. They monitored every crossing. The demonstration went perfectly. The locomotive performed flawlessly, pulling its massive train with the kind of effortless power that made spectators actually gasp. But after it passed, bridge inspectors found microfractures in 3 stone arches. Nothing immediately dangerous, nothing that required closure. Just the beginning of structural damage that, if repeated regularly, would cost millions to repair. The Pennsylvania faced an impossible choice. They could continue using their engineering marvel and systematically destroy their own infrastructure, or they could sideline a locomotive that cost hundreds of thousands of dollars to develop and represented years of engineering work. They chose a third option: restrictions. The locomotive was banned from certain bridges entirely. Speed limits were imposed on others. Routes were carefully planned to avoid the oldest, weakest sections of track. The machine that was supposed to revolutionize freight operations became a routing nightmare. A locomotive that required special handling, special permissions, special inspections before and after every run. And still, the damage continued. Not catastrophic, not immediate, but persistent. Rail crews working sections where the heavy locomotive ran regularly reported unusual wear patterns, ballast crushed to dust under the repeated hammer blows of those massive drivers, subgrade settlement in areas with poor drainage. The locomotive was leaving a trail of maintenance headaches everywhere it went. By mid-1945, the Pennsylvania had quietly pulled the locomotive from regular service. It made occasional runs, carefully planned and closely monitored, but the dream of using it to replace multiple locomotives on heavy freights had died. The machine sat in roundhouses more often than it ran, a monument to the law of unintended consequences. Other railroads watched and learned. The Union Pacific, already dealing with weight issues from their own massive locomotives, quietly shelved plans for an even heavier machine. The Norfolk and Western, famous for engineering brilliance, stuck with their proven designs rather than chase absolute power. The lesson was clear. There's a point where more becomes too much, where engineering excellence creates operational impossibility. The irony was brutal. The locomotive wasn't a failure. It was a success that succeeded too completely, that achieved its design goals so thoroughly that it became unusable. Every system worked. Every specification was met. And yet it couldn't perform the job it was built for because the infrastructure couldn't handle what the locomotive could deliver. Consider the mathematics of the problem. American railroad track in the 1940s was generally designed for axle loads around 70,000 to 75,000 pounds. The Pennsylvania's monster put 105,000 pounds on some individual axles. That's 50% more load than the infrastructure was built to handle. Spread over 6 axles instead of 4, the total weight was manageable, barely. But at any given point where an axle contacted the rail, the forces exceeded design limits. Track isn't just steel on wood. It's a system. The rail distributes load to the cross ties. The cross ties distribute load to the ballast. The ballast distributes load to the subgrade. Each component has limits. Exceed the limit at any point, and the system begins to fail. Not explosively, not immediately, but progressively, inexorably, like water whirling away stone. The Pennsylvania tried reinforcing track on main routes. They installed heavier rail sections. They replaced wooden ties with concrete in some areas. They improved drainage and rebuilt subgrade in problem sections. But the costs added up fast. For every dollar saved by using one locomotive instead of 2, they spent $2 fixing the track it ran on. By 1947, the locomotive's fate was sealed. The Pennsylvania had newer, lighter locomotives coming online, machines that sacrificed some raw power for operational flexibility. The heavy giant was relegated to occasional use on specific routes where track conditions allowed. Engineers who'd worked on its design moved on to other projects. The machine that was supposed to transform freight operations became a footnote. What makes the story remarkable isn't the failure. It's the precision of the failure. The locomotive didn't break down. The boiler didn't explode. The running gear didn't seize. And every mechanical system performed exactly as designed. The failure was systematic, infrastructural, economic. The railroad had built a machine too good for its own railroad. There's a broader lesson here about engineering and systems. We celebrate innovation, breakthrough performance, revolutionary designs. But innovations exist within systems. A locomotive doesn't run in isolation. It runs on track, over bridges, through yards designed decades earlier for different machines. Revolutionary performance in one component can create revolutionary problems in the system. The Pennsylvania's experience rippled through the railroad industry. Later, locomotive designs paid as much attention to axle loading as to power output. Engineers learned to think about infrastructure limits as hard constraints, not suggestions. The golden age of ever larger steam locomotives ended not with a bang, but with a quiet recognition that bigger wasn't always better, that sometimes the most powerful answer wasn't the right answer. The heavy locomotive itself? It survived into the early 1950s. Making occasional appearances on freight runs where conditions allowed. Crews who ran it spoke of its power with a kind of reverent awe, the way it could lean into a grade with 12,000 tons and just grind upward, the deep exhaust bark that sounded like artillery, the sensation of controlled violence as 6 sets of drivers hammered the rails. But they also spoke of the restrictions, the routing headaches, the inspection requirements. One engineer, interviewed years later, summed it up perfectly. Best locomotive I ever ran. Worst locomotive to run. By 1952, the Pennsylvania quietly scrapped it. No ceremony, no preservation, just a trip to the cutting torches and the scrap yard. The railroad kept detailed engineering drawings and test reports. The knowledge was preserved, even as the machine itself was destroyed. Those drawings served a purpose. They showed future engineers exactly what not to do. Today, railroad historians debate what might have been if the infrastructure had been stronger, if the track had been newer, if the bridges had been designed for heavier loads. Could the locomotive have revolutionized freight operations? Absolutely. Given the right system, it would have been transformative. But it was built for a system that didn't exist. A railroad that existed only in engineering calculations, not in the real world of aging bridges and track laid down when locomotives weighed a third as much. The final irony? Modern freight locomotives routinely exceed the tractive effort and pulling power of the Pennsylvania's heavy giant. They do it with distributed weight, multiple units, sophisticated control systems. They do it by working within system constraints rather than against them. The power the Pennsylvania sought in one massive machine now comes from networks of machines working together. The train that was too heavy to run wasn't an engineering failure. It was an engineering success that revealed a deeper truth. Sometimes the limit isn't what your machine can do, but what the world can handle when your machine does it. The railroad companies that refused to run it weren't being timid or short-sighted. They were being realistic about the difference between what's possible and what's practical. In the end, the locomotive achieved a kind of immortality anyway, not as a preserved machine, but as a cautionary tale told in engineering schools and railroad offices. Build for the system you have, not the system you wish you had. Respect the infrastructure. Understand that every technical triumph exists within constraints, and sometimes the smartest engineering is knowing when to stop pushing. The train so heavy railroad companies refuse to run it remains one of railroading's great what-ifs. What if the track had been stronger? What if the bridges had been newer? What if the entire system had been built to handle such concentrated power? But those questions miss the point. The system wasn't built for it. And in the real world, that's all that matters. The rails remember, though. On certain sections of the old Pennsylvania main line, track engineers still find unusual wear patterns in the rail, stress marks that don't quite match normal traffic, ghosts of a machine that was too powerful for its own good, too successful for its own survival. A reminder that in engineering, as in life, sometimes the most impressive achievement is knowing when you've gone far enough,